on? Good morning, everyone. Welcome to Building Einstein. We're going to talk about multi-app, multi-tenant machine learning at Salesforce scale. And before I get started, though, the obligatory forward-looking statement slide. You'll see this at the beginning of every one of the presentations here. Please don't make any purchasing decisions for Salesforce products based on anything you hear today, because we might talk about products that we have not yet released. Please make those decisions based on generally available products that you can find at salesforce.com. With that out of the way, my name is Richard Pack, and I'm joined on stage by my coworkers, Kevin and Michael.
Hello.
And unfortunately, Leo could not be here today. So building intelligent applications that are using deep and machine learning are not that easy to build. There's just a lot of things that we have to think about, starting, not least of all with how do we handle security, how do we do the data acquisition, the data prep transformations, building base models, training those models, then iterating over a tuning, generating the predictions, pushing those predictions back to a system of record, building the user interface for those, to show those predictions in an application and putting that all together as a single product. But doing that at Salesforce means that we have to put these models into hundreds of applications and then deliver high-performing models to each one of our customers, at least one per application. So that's actually a really hard problem, a very, very hard problem. And what we have to do here is actually build a bunch of machinery, or an automation, if you will, that builds the machine and deep learning models, and does that with as minimum human interaction as possible, because humans don't scale as well as the algorithms do. So, automating the integration of AI into apps is how we actually solve delivering these hundreds of thousands of models to our customers and ensuring that they actually perform well. So we have to do a lot of automation around how and when we acquire data, we transform and prepare that data, how and when we do the training and retraining. We do criteria and threshold-based model deployment. We have automation around the inference generation based on data change events. And the automation of how we actually take those inferences and then write them back to CRM schemas, and then show all those factors into the UI. So, and we had to do this kind of just once in terms of a platform, so we can have the power of this platform help us build these very, very quickly. So all this automation that we've built is behind a single API. And this API is the API that we use to reference machine and deep learning models in our products. And it has three parts. The first part of the first three endpoints here, there are the application defs, the prediction def stands for definition, and the model definitions. And the application is basically just the container for one or more models. A prediction talks about what problem we're trying to solve on what data set. And then a prediction can have one or more model definitions. And the model definition contains all of the hyperparameters and any of the test train splits and all the ML or DL specific characteristics. And then once we create these, we do a post on each one of these endpoints. Out the other side pops a model or a set of models that we can do predictions on. So I'm going to go ahead and do a quick demo. I'm going to use Postman, and I'm going to build. We have a GA product called lead scoring, so I'm going to go ahead and build. Show you kind of in a demo way how we built lead scoring using this automation and API. So I'm going to do it from a video because we're time constrained with this. So here we have Postman. We're going to create an application, a prediction definition, and a model definition in the three tabs at the top here. So like I said, the application is just a shell. We just give it a name and a status. And in this case, the status is referring to enabled. There's two statuses, enabled and disabled. Enabled just means once we create this and the entire configuration is valid, please go ahead and train a model. So I'm going to take the ID after I create it, and then I'm going to put it into the URI of the prediction. And then I'm going to talk about the post body for the prediction. So like I said, the prediction deals mostly with data and the type of machine learning problem generically we want to solve. So here we're going to work on a binary class. We're going to create a binary classification problem. We're going to use the target field or the response field. This is the set of labels that we're going to predict. In this case, there's two, whether or not this lead converted. So we're actually trying to predict the quality of the lead. And then we're going to write back the outcome to this custom pushback field. And then we're going to exclude the last modified by ID because it's not relevant, really. This is just an example of what we can exclude. It's not relevant to the machine learning problem we're trying to solve here. And we're going to there's a filter at the very bottom here, and the filter just basically says only work on the default record type. So I'm going to go ahead and create that prediction definition, and I'm going to take both of these IDs and put them in the URI for creating a model definition. So here, some machine learning specific things. We have a 60-40 train split ratio, and that we are going to only look at leads that have values in the industry field of 1 of 4 values, then agriculture to banking. And as soon as I post this, that concludes the demo. And what happens right after this is that we go ahead and we acquire the lead data for this filter that we specified. And once we acquire the data, we begin the training of the model. So we automated the data pipeline too. So like I said, the next step after you saw that is that we go and acquire the data, and we can pull it from multiple data sources, both internal to Salesforce and external connectors. And they come in 2 forms: the change data capture stream, which is the change events for the records that are in the system of record, and that batch that we can query and extract large volumes of data, and then we can bring it into our ETL tool and prepare all that and store it all in the machine learning data store, the multi-tenant data store, and it is now available for training and scoring. So we also want to let the data scientists focus on models and model quality. And in order to do that, we really need to figure out a way to automate as much as possible around managing just the sheer number of models that we have to deploy. So like I said, if we have a single product and each customer gets 2 models, and we have thousands of customers, we have 2 times that many models that we have to manage, right? So we have to support a lot of features like health-mediated deployment, meaning that if we try to push a new model as an experiment, and we can say like if it performs worse by some measure or some set of measures, that we don't want that to actually move to production. We have to have an experimentation framework where we can do these comparisons across the historical set of models that we've created, and also be able to push multiple models. Like say we want to choose 10 different values for a hyperparameter. We can see which one performs the best, and then we can push that into production. And we also want to automate and have criteria-based rollout of retraining, of model activation, and don't write the predictions back if the predictions don't have a very high accuracy. So with that, I'm going to pass it off to Kevin to talk about AutoML.
Great. So speaking of letting data scientists focus on training the models and doing data science, hi, my name is Kevin. I'm a senior data scientist on the Einstein team here. And Michael and I are going to talk a little bit about more under-the-hood aspects of some of the auto machine learning stuff that we use here at Salesforce, some of the problems that we have, and some of the solutions that we've developed to address these problems. And so this is really like an end-to-end set of automation for machine learning. We have to automate how we're extracting data from the raw Salesforce data and whatever objects we want to make predictions on. We have to automate picking which features we want to keep, which features we want to throw away, which ones are predictive. We have to automate picking the right model for the right problem and the right settings for that right model. And so we'll step through each of these one by one and go through a little overview and a code example of how our platform actually solves this. So to start out, the first step is to generate actual features from the raw data. And what we mean by features is we just mean numerical data from a wide variety of data types that are sitting in Salesforce. And so we have to generate numerical data before we can feed that data into a machine learning algorithm and actually train and deploy a model. But because we have such rich data type information in Salesforce, we can do different feature transformations and different extractions depending on the type of the data that we're dealing with. And so some of these can be really simple. Some of the data already starts as numeric, so it's relatively easy to transform it into a form that the algorithms are happy with. Other things like texts and emails, phone numbers, categoricals, it's a little bit more involved. And so I'll go through some of the examples of some things that we do with commonly used types. So for example, with emails, we can do things like spam detection, check whether or not this is a spammy-looking email address. We can do things like pivot out the top 10 or top 20 or top however many we need email domains. For phone numbers, we can do things like grab the country code to cross-reference with geolocation data. We can do checks on whether or not this is actually a valid phone number based on that country code. For numerics like company size, we could just use them as is, but sometimes it's also useful to bin these in different buckets. And so these buckets can be determined at runtime from the actual data. They don't need to be determined beforehand. This would be an example of some, if a tenant was targeting smaller size companies, you might come up with a split like this that might be useful, but different company or different use cases might require different splits. For text data, it's a little more complicated, but you can do things like top TF-IDF terms. You can do automatic language detection, which is extremely important for all of our use cases because we're often dealing with customers from all over the world and large multinational customers that might have a wide variety of languages in their own data. And so we can't just assume that we're doing English text processing techniques. We have to actually do text processing techniques appropriate for the language. And finally, we can do leverage external data like average incomes, populations, weathers, things like that from zip codes. And so combine these all together into a feature vector, and then we're finally ready to start passing this on further down the pipeline. And so to describe a little bit more about how we do this in the code is Michael.
Thank you, Kevin. So hi, everyone. So I'm Michael. I'm a data scientist at the Einstein team of Salesforce. But first of all, let's start with a demo. So what I'm going to do here is train a model for lead scoring. So I'm training a model on some lead training data. So actually, I'm going to show you the data. So this is the data here, like typical lead data. Our goal of our training is to predict whether a lead has been converted or not. So this is what we call the response. Also, maybe a disclaimer. So as you can see here, this is a spreadsheet of the data in my laptop. But don't worry, this is not real customer data. Like if you look at the name here, like you can see our names, you can see Mark Benioff names. Those are not real leads. So this is definitely fake data. But in general, for us data scientists, it's not possible to have real customer data like that on spreadsheet in our machine. I think you all know that our first core value at Salesforce is trust. And like if you're looking at the news, there are some other companies right now that are having issues with trust, let's say. But like us, at Salesforce, we really care about trust. So that's why it's not possible to play with real customer data like that. So it's only for the demo. So this training is done on the AutoML library me, Kevin, and other people on the team have built. It's called OP. So it's an AutoML library built on top of Spark. It's in the phase of being open source this year. So after the talk, you can talk to Mayuk right here. He's actively working about open sourcing the library. Yeah. So don't worry. At Salesforce, Spark is not the only stack we have for machine learning. Like I know that other teams within Einstein are like developing ML tools using TensorFlow, for instance. So it's not only Spark, but we decided to choose Spark because of the distributed computing, which is pretty good. Like, and they have very nice data structure, like RDD's data set. Also, they provide a built-in machine learning library called SparkML, which is very good to use because we have already built-in components. And last thing is like Spark is pretty active. They have a pretty active community. I know that at least every year we're doing at least 2 releases, I'm pretty sure. So, so the training is done. We built a model, but I'm gonna talk about the result later at the talk. So about feature engineering, to deal with this issue, we created in the library something called features, sorry. So feature basically is a pointer to a column of a Spark data frame. And to do our feature engineering, we're also providing lots of types that we have created. Like, very example, we created type like email, phone, also generic tag like integral and text. And the feature engineering is done with this magic function you can see in the end. It's called vectorize. And what vectorize do is, in this example, it will map over our feature. If for each element of the feature, it will do the right feature engineering based on the type of the feature. So you say, oh, this is a phone, feature of type phone. So it will do the feature engineering by looking at the country code to check if it's valid and so on, etc. So after doing that, after mapping and do the feature engineering, it will combine into a feature vector. So it is a very good first step, but it needs more to be done. So Kevin is going to talk about feature selection.
Okay, so now that we have some features generated, we need to actually check, are these useful features for the problem? Are there any bad features lurking in the data that we want to exclude automatically? And so because we've already converted everything to numbers, we can do a lot of summary statistics on this type of data. We can calculate things like min, mean, max, variance, how often the field is empty. We have various imputation strategies that we use for filling in missing data. As I'm sure you noticed on the spreadsheet, there was lots of missing data in there. We can calculate how related the fields are to the labels by calculating things like mutual information between a variable and the label, correlations, stuff like that. And so we can check if the features have acceptable ranges. We can check for validity of certain features depending on their type. And we can ask, does this feature help our model? Is this feature actually predictive? Do we actually want to use it in a machine learning model? And because we're dealing with lots of custom data, a ton of fields that we deal with are custom fields created often in custom objects by customers. And we need to monitor, are these fields have they been around for a while? Do we have enough baseline data to actually include them in a model, or are they relatively new fields that have been added? Has their use changed over time? So these are all things that a data scientist would look at when they're actually building a model by hand that we have to automate here because we're dealing with hundreds and hundreds of thousands of models. So in addition to selecting the best features to use, we also want to get rid of the bad features. And this is very important. And I think the best way to illustrate this is with a little example with the predictive lead scoring case that we've talked about. And so remember, this is to just basically make a prediction on the quality of the leads. We're mostly interested in a ranking at the end. And so some examples of things that might be bad features, depending on a customer, depending on some or their business processes. Let's say there's a field like deal value that gets populated once a lead is close to being finalized. If you throw that into a machine learning algorithm, it will say, hey, whenever I see this deal value, that means this is a great lead. And whenever I don't, probably not a good lead. But that's not actually a predictive value of whether or not the lead is of high quality or not. That's just an artifact of the business processes used by this business. So you don't want to use that heavily in your model, and you don't want to report that back as a strongly predictive factor. Similarly, there's lots of data that isn't available until the label has been determined. So in this case, once the lead has either been lost or converted, there might be auxiliary fields that you fill out, like reason lost. Why was this lost? It could be a categorical, it could be free-form text. Converted by might be a reference to the sales ID of the person who was working on this lead. And so again, if you just throw these in naively into a machine learning algorithm, they'll say, hey, these are great features. Whenever I don't need any other features, I'll just use reason lost and converted by. Because when you're training the algorithm, you have these labels available, and any algorithm would rightly pick up that these are great features, but these are never available at scoring time. These are never available before you know the label. And so again, this would make the result of this is you'd have models that would perform really poorly on unseen data. And again, this is problems that a data scientist would need to do by hand when they're creating these models that we have to automate here. And this is extremely important when business processes are unknown. So especially with products like Einstein Prediction Builder, where we're working with unseen data, predicting an unknown field, we don't know necessarily what any of the business processes is. So we have to have a lot of investigation here into and automated ways of detecting and throwing out bad fields. And so to show, again, an example of feature selection is Michael.
Okay, so what I'm going to show you is an example of a bad feature. So back to the data. If you look at field called deal value. It's a custom field, but no matter. This is what we call a leaker. So the definition of a leaker is a field that has seen the response before, which here is converted, so that it is super predictive. So first, we can see that it is indeed super predictive. Why? Because like if this field is defined, like here and here, you can see the response will be true. If it's not defined, if it's missing, it will be false. But the reason for that is that these values you can see here are only available once the lead has been converted. So that's why we say that this field has seen the response before. So usually the risk for a data scientist, if he is building a model by keeping the feature, the model will learn this implicit rule saying that if the value exists, then the response will be true. And the risk when the model will try to predict unseen data, new leads. For the new leads, this field will be empty, for sure. And that means that the model, based on that rule, it will see that it's empty every time. It will always predict false. So that's why it's a bad feature. So it's up to the data scientist to do some data exploration to figure out which feature or bad feature are good features. But here we want to automate the process. So we have a magic function here called check. It's checking if the feature are good or bad feature. So what it does is for every feature, it will compute lots of statistics. And based on those statistics, it will check if it's a good or a bad feature. If it's a bad feature, we'll remove it. So I can show you an example on the command line I ran before. I can show you the statistics in the logs. So those are the statistics we're computing for each feature. We can see the mean, the variance, and also other statistics, the correlation, other statistics related to pick lists, multi-pick lists, like the pointwise mutual information, or like the statistic called Kramer's V, if I can see here. Never mind. And what is interesting here is which feature have been dropped. So it's here, the feature drop, and you can notice that our leaker, lead value, has been dropped by our magic function. So we have some feature vector that has been feature selected, and now we're ready to proceed to modeling with Kevin.
Yeah. So now we've got features. We've got features that we've convinced ourselves are not crazy features to use in a model. So the last step is actually training a model and picking which model to deploy. And so I'm sure you're familiar that there are many different machine learning algorithms out there. And each algorithm has a ton of tunable parameters. So the question that we have to ask at this point is which settings and which machine learning algorithms are appropriate for each task. And so you can imagine this as, if there were only 2 parameters, and you could visualize this, you can imagine that there's some objective function that you want to maximize. So basically a goodness of model metric that you can calculate, and you want to find the best point. So you want to try a lot of different models, and you want to find that point in the upper right corner and not use models that are in less good areas of feature space, if at all possible. And so a general strategy for this always boils down to computing a bunch of different models and evaluating them, and then using that information to find the optimal hyperparameters, the optimal models, and the optimal settings. And there's lots of different ways of doing these model trainings and combining them into figuring out what the best model and what the best hyperparameters are. You can do things like simpler things like grid search and random search. You can do more complicated things like bandit-based methods or Bayesian methods, and which one you use basically can depend on the problem that you're attacking, or basically how many features or how complicated your model is. And so the idea is just train a bunch of models and pick the best performing one on this data. And it's not always going to be the same model. So an example of what you might get if you're training lots of different models with different hyperparameters is this graph that's measuring the accuracy of different models with different parameters. So the colors here are indicating the actual algorithm type. So the type of model that we're training, this could be random forest. GBT stands for gradient boosted trees. It could be a normal decision tree, a logistic regression model, a naive Bayes model. There's tons of other options. This is just a sampling. And then the different bars with the same color would correspond to the same model type, but with different settings, different hyperparameters. And so you can see that there is, even without axes on here, you can see that there's a big difference between the performance of some of these models. And in this case, a random forest happened to be the winner for this data type, or for this set of data and this problem type, but that's not always going to be the case. We have to do this on a per tenant basis, and because sometimes logistic regression will win, sometimes gradient boosted trees will win. And so to actually show what that looks like in practice, again, is Michael with the code.
Okay, so to complete our AutoML stack, we implemented something called the model sector. So it does what Kevin said. It will try different model and pick the best one with the best set of hyperparameters. So here on the line, you can see like we're using model sector by training these models, logistic regression, random forest, and gradient boosted trees. And the output of the model sector is that the score we want to get after training. I mean, what the models need to output. And to train the data, we set this score feature into something we call workflow. And what it does at the last line, workflow.train, it will look at this feature, pred, and we'll figure out what the DAG was necessary to get the feature. So we say, oh, to get pred, I'll need first to do the feature engineering, then you need to do the feature selection, and then the model sector. So it will automatically figure out the DAG to build that feature for the model. When the model wants to score new unseen data, it will do that. And so I'm going to show you the results in a terminal. So if I'm looking, let's try it here. So as you can see here, those are all the models the model sector tried. So this is a random forest here with this set of hyperparameters. This is another one with different parameters, but also it tried logistic regression here and so on. So lots of models has been tried. And I'm going to show you what was the best model. Here. So the best model was actually a random forest with this kind of hyperparameters. So for instance, with number of trees of 50, with number of the maximum depth of the tree of being 12, and so on. So that's great. Also, what is available are the training metrics here. So maybe some metric explaining to you, like this one, error. It's basically the error rate of your classification. Other metrics we can look at are like very specific for binary classification, like true positive. Positive here for lead scoring is like field that is being converted, and the true positives are the number of this positive that were correctly predicted. And the same goes with true negative, false positive, false negative. And there are other binary classification metrics like precision recall, AURC. Don't pay attention to the metrics itself, like because we did the model on some fake data, so the model is not great. We're not using model at Salesforce on fake data. Don't worry. Okay. So that's it. Back to these lines of code. So we can see here the magic of AutoML, because this is an example where most of the work and decision making made by a data scientist can be automatically done with these few lines of code. And also we can imagine that these lines of code can be reused for other tenants who want to predict lead scoring. So it will be the same, but the AutoML, the outcome of the AutoML will be different. For instance, the feature engineering will be different based on the data and so on. It will probably remove other feature for another customer, and maybe for another customer, the best model was, I don't know, actually logistic regression compared to what we got before, like a random forest. So yeah, so this is what's happening under the hood in terms of the ML. And Kevin is going to talk about what's outside.
All right, so to wrap it up, now that we have a model, the last step is to actually use that model, deploy it, make predictions. Again, these aspects are also automated. We can have batch scoring, where we would pull data with a certain cadence and then score on all those records that we pull. We can have streaming scoring. We can have on-demand scoring. So what's important here is the same data transformation that we did and discovered was useful in the model training phase. The same exact transformation has to be done on the data before we score it. So we have that same data transformation step. We have to have a way of storing the exact transformations we've done on all the features in the model. So that's stored with the model. We then can generate a prediction and automatically push it right back to Salesforce. And we can also do more complicated things like push back things only if the score has changed in a certain threshold, listen for updates in the records before actually pushing updates to scores, things like that. And finally, as Richard mentioned, this is all behind an API, and this is all configuration-driven. So again, you can specify all of these aspects that we are automating with a config. You can define the field that you want to predict on. You can define the object that this is working on. You can define any fields that you want to exclude, filters that you want to use for both training and scoring, any kind of training scoring split you want. And you can use that, and everything works behind the scenes, and we'll give you predictions back. So we've got like 8 minutes left, but I'd like to thank you, everyone, for coming out to our session, and we'd be happy to answer any questions that you might have.
Hello.
Can you use that mic? Just to, oh, isn't that work?
It is? Okay, thank you. You guys talked about trying different models to find the best one, the one that would predict the best. And my question, and I might have missed that, how do you know it's the best?
What's that?
How do you know it's the best model? How do you know you have the best
How do you know there's no other better model out there?
Or what's the measurement?
Exactly.
Yeah, okay.
Okay. Do you want that?
So what's the measurement? So the user, we can specify which metric is the best, so we can choose, like, I mentioned you the binary, here it's binary classification metric, like a URC. You can say, give me the best model based on URC, and we do that by doing cross-validation, and we return that the best average cross-validation metric. So we compare that on the same cross-validation.
Yeah, so it depends on the type of problem that you're doing. So a binary classification task, you'd use different metrics to optimize than if you were using a straight regression or prediction, like a numerical prediction type problem. And so these are actually configurable. The metric that you use to decide the model is actually configurable in the config that I showed at the end. It's kind of a challenge on how to expose that in something like Prediction Builder, because you don't want to have like a drop-down menu. Like, would you like area under ROC or area under precision recall curve as your way of determining models? So we're experimenting with things about like communicating whether or not, or having the users communicate whether or not, false positives or false negatives are worse for whatever problem they have, and then using an appropriate metric based on that. So with all those metrics that you saw at the end of the model run, there are ones that are sensitive to different types of misclassifications.
Yeah. So this is, it's for classification. For regression, I forgot to mention, we have other metrics like mean square error, adjusted R-square, and so on. The usual regression metrics. So it depends on the problem. Yes.
Another measurement question. What do you use to determine which predictor to drop? Is something like p-value? What are you exactly using? Because there's a bunch of them out there.
It depends on the variable type a lot. So you're talking about like how to detect the bad features that are too highly, that we think of scene label information?
So you showed the deal value, right?
Mm-hmm.
You know that gets filled up when you're a day away from it.
Yep.
How would you know what measurement to use to determine
Yeah, so for that specific one, for deal value, you can basically just look at the null indicator, basically how often that field is null, and check the correlation of, you can do all sorts of statistical tests on the real valued fields. So for example, real value fields, we can compute Pearson or Spearman correlations and say if like, hey, if we notice like a perfect correlation between the value and the label, get that out of here, that's not a real feature. For categorical variables or things that are encoded with null indicators or one-hot encoded, we can do categorical tests that are based off chi-squared tests. So there's a quantity called Kramer's V that's basically a notion of correlation between two categorical variables. We can do things that are similar for like multi-pick lists, which can have multiple values selected, so it's kind of like categorical but more complicated. Yeah, there's a whole variety of stuff, and it kind of depends on the type of the variable, and also whether the field, the label that we're predicting is continuous or discrete.
Yeah, I don't know a lot about what we're talking about here, but let me ask a question. I'm a data guy. So if you think about leads, can you do anything about related data that might help you predict what's happening with the lead, like the number of activities in a certain state for a given lead might be prediction? Can that be
aggregates as
factored into the
features?
model?
Yeah. Yeah, we can do that as well.
Mm-hmm.
Yeah.
Yeah,
That's
so
actually something we do with lead scoring. We just didn't demo that part. So.
Yeah, so we actually do have support for all sorts of complicated joins that you can do with the data in the library that we have, and some of that is in use right now in Marketing Cloud. And so that involves pulling multiple tables of data and joining them in ways to basically get that kind of activity data. And so yes, we are investigating ways of doing that with basically all Salesforce object types.
So how does the model change? Say I have like my initial import of data. Does the model change like once I import like, a lot more? Does it continuously update, or is that something?
Yeah.
Yeah, one of the retraining triggers is the amount of data that's changed since it's been retrained. So just a number of rows compared to the original data set. And so whatever the training window was, say it had 1,000 rows and you just added another 1,000 rows. That's going to trigger a retrain. So there's time-based triggers as well.
Yeah, there's a few different strategies that we would use to retrain models. So sometimes we'll have a fixed cadence that will say if the model, even if we don't have any reason to expect that things have changed, just every month, let's make a fresh model. It's not going to hurt anything. Other cases, we can do things like, if we have enough data, we can do things like performance monitoring and check how the running metrics of the model in production are. And if we notice like big drops, we can trigger an early retrain. And again, we can also monitor for like bulk uploads of data and trigger a retrain in those circumstances.
Yeah, and field addition and deletions as well. So schema changes would also do a retrigger.
Yep.
That actually might lower the performance of the model in some cases.
Yes.
Did you try to use your own data prediction to also like predict what are the models that are the best or that kind of things? Like a meta model of the field, how you should do it?
Not, but we're like really considering the idea of like doing some offline learning and that involves some meta learning from that. So we're working on it right now, but I cannot say more about it. Yeah.
Yeah, there are things in the works.
Okay.
Awesome.
Anything else?
1 minute left.
One more, I guess.
One more? All right.
Maybe this is just built into different models itself, but it strikes me that maybe data might fall into different categories. Like what predicts a lead would convert for a small company might be different than what a lead would convert for a large company. Mm-hmm. How would that factor into the model and learning and stuff?
So that could factor in a few ways. The most direct way that could cause a difference is on completely different data. Let's say it was the same exact object, so it was still a lead object, and let's ignore custom fields for now. So let's say all the feature engineering is the same. The model selection could still be radically different between the two orgs, and so if there's enough actual predictive data in both of those orgs, then the machine learning algorithms should recognize that different fields are predictive in one case, or different areas, or like different binned values of fields might be predictive for different orgs for different purposes. So that's kind of this let me go back here. That's kind of this whole idea of, oh, you can't see it, never mind. That was the whole idea of that, like showing that surface of like finding the best place for the model, and so that's done completely separately for each tenant. We do that, we start that process from scratch.
I guess my question is, there are orgs where you've got, users that are targeting both, not different orgs, but in one org you've got one set of users that are targeting small,
Yeah,
or large,
so
or you've got some,
there's
in
a
the
like a
population.
canonical example of territories. So a sales team targeting 2 different territories. The sales team have different behaviors, but they still use the same opportunity object. They still, so all the objects are the same, but the behaviors are different, so the data has different shape. So so like I said in the very beginning of the presentation, we sometimes generate multiple models. So we try to find those natural pivots. Territory is one of those, where we can we can create a model per territory. So.
Okay. Maybe no more question. Maybe
Okay.
one last question.
All right.
So in order to use Einstein, do we have to have our data physically in Salesforce, or we need to, if we have another source of data, do we need to copy it and physically store it in Salesforce or not?
Either one. There's the Einstein Discovery product. It's agnostic. So there's 14 or so data sources it supports.
Yeah.
Okay.
Yeah, it depends on the prediction type.
It depends on which product.
Yeah.
Yeah.
Right.
Yeah. Some of them you do need your data in Salesforce.
Yeah.
Yeah. Okay,
Okay, great.
great. Yeah, thanks. So yeah, we'll
Thank you,
stick
everyone.
around and answer questions personally, but we're like a
Yeah,
little
yeah.
over time. So yeah, thanks everyone for coming in.